This problem says find the interval of convergence. So first thing we're going to do is ratio test. So here it is. Rho equals the limit as n goes to infinity of a sub n plus 1 over a sub n, which is going to be the limit as n goes to infinity of 2x to the n plus 1 over n plus 1 divided by 2x to the n over n. Now, what we're going to do now is we're just going to flip that bottom, and I'm going to write it in a different way as well. So hopefully you're okay with that. So this 2 to the x to the n to the 2x to the n plus 1 is really 2x to the n times 2x. And then n plus 1 on the bottom times. And then on the top, I'm going to get n over 2x to the n. Okay, and then I can see that those cancel out. So what I really have here is the limit as n goes to infinity of 2xn over n plus 1. And since the 2 and the x are not the variables I'm taking the limit of, I can treat those as a constant, which means I can pull them out front. So this is really just 2x times the limit as n goes to infinity of n over n plus 1. And then I can use L'Hopital's rule there because I get infinity over infinity as my n goes to infinity. So then that's going to be 2x times the limit as n goes to infinity of 1 over 1, which equals 2x times 1, which is 2x. So there's our answer for this one so far. But I know that this 2x means that the absolute value of that has to be less than 1. So that implies that 2x is between negative 1 and 1, which implies, x is between negative 1/2 and 1/2. Now we're going to have to check for, is there equality for any of these 1/2s, either the negative or positive 1/2. So now to do that, we're going to have to take those values there. So remember, this says x is between negative 1/2 and 1/2. And we want to see if that x can be 1/2 or negative 1/2. So what we do is we take the original series and we plug in. Let's do the negative 1/2 first. So that's going to be 2 times negative 1/2. And then that's to the n over n. And if this series converges, then we include that negative 1/2. If it diverges, we don't. Okay, so now this is going to equal the series n equals 1 to infinity of negative 1 to the n over n, which this is really, and I'm just going to write this another way and you guys will see what I mean here, if you don't see it already. This is the same series, and this converges, doesn't it? And I would be okay with you saying this converges because it is the I'll just write it over there. Alternating harmonic series. So this means, since this converges, that has to be in my interval of convergence. Interval of convergence, that means it's included. So that negative 1/2 is included. Okay, so now let's play around with that other side now. So the series n equals 1 to infinity of 2 to the positive 1/2 now, because we're checking this other side now. Okay, and that's all to the n over n. And once I clean that up, I get n equals 1 to infinity of 1 to the n over n. Now this one is similar to the harmonic series. So for this one, and most of these we'll have to go through some process. If we did the ratio test on this one though, we would get inconclusive. This gets a little bit hairy with this problem here. So I would be okay with you guys just saying that this series diverges, because it looks similar to the harmonic series. And the harmonic series we know diverges because it's a p series and our p is 1 here. Remember, where it was less than or equal to 1, then it diverges. So it diverges. I would be okay with that here. Okay, so then this one diverges, so we don't include the positive 1/2 here. So let's write this interval of convergence out now. So that interval of convergence includes the negative 1/2, so I use a bracket. Remember, a bracket means it includes it to 1/2, and I don't include the 1/2, so I use a parenthesis there. So this would be our answer for this problem.